Square waves have been used for years in the development and testing and measurement of amplifiers to test the rise and fall time of a transient. And as you approach towards that perfect square, you're improving the timing and delivery of those transients, and so you're essentially reducing distortion and improving the clarity and transparency of sound.
We'll be testing a speaker cable. Here we have the input to the cable, and the cable goes off the table and spools into a box, and then it comes out and enters this board. First, we have a signal generator that's generating the square wave. We're generating a 10 kilohertz square wave, and this cable feeds the signal to this high bandwidth amplifier. This amplifies the signal, which is then sent out the cable, and then the signal comes back into the board where we can examine it with the oscilloscope. We're using a 100 megahertz Tektronix oscilloscope to look at the signals. All right. I have 4 micro circuits in my hand. Together, these comprise the electric field compensation circuit, which is the core of the Zytron technology. We have specially modified this cable with micro connectors at each end of the cable so that we can demonstrate in real time what the technology does. So we'll be able to actually plug these circuits in and pull them out, and you'll be able to see on the oscilloscope what it actually does to the signal. So we have 2 channels that we're going to look at. We're going to look at the output of the amplifier, the input of the cable. So I'm going to connect the scope probe to the wire. Like that. We'll connect to ground. And then this probe, so you see the yellow trace is the input to the cable. Now I'm going to connect the blue trace to the output of the cable. There we go. So, as you can see, now at the end of the cable, this is what happens to the signal. At the end of the cable, you'll notice that the signal is considerably rolled off on the rise and on the fall of the square wave. And what this indicates is that the cable is either absorbing energy or keeping high frequency energy from being transmitted through the wire. Now, we're going to start to insert the electric field compensation circuit. So I'm going to insert these elements into the cable one at a time. There's 4 of them, and you won't really see the total effect until we've completed the circuit with all 4 of the elements. So I put the first 2 in, and now I'm going to complete the circuit by putting the last 2 elements in. And you'll notice that the blue trace is starting to change. And when you look at the scope, you can see that the signal at the output of the cable now more closely resembles the signal that we fed in to the input of the cable. So just to make that clear, I'm going to pull these 2 elements out, which will disable the circuit, so you can clearly see the blue trace, what it's like without the Zytron technology. Here we go.
If you were able to effect that level of difference as an amplifier manufacturer, you would have done something truly significant.
We have the patent application which people can look at, and they can see the specifics of what we're doing. Essentially what we're doing, it's a little complex, but essentially what we're doing is we're splitting the magnetic wave and the electric wave, and we're sending the magnetic wave and the electric wave independently down the wire. So once you make a paradigm shift in technology, then the little things that you used to do to refine a product become almost insignificant. I like to use the analogy of a World War I biplane. You can change the structural components of the plane. You can change the pitch of the prop. You could put a more powerful piston engine in it, and it makes a difference. And the analogy is, in the cable industry, you can change the stranding of the wire, you can change the number of nines of the copper, you can change the insulation materials, you can change the geometry, and it doesn't make a difference. However, once we developed Zytron technology, we now have the equivalent of a jet aircraft compared to a biplane for the old technology. I spent a lot of time in the military working for a division of NSA. It was called the Army Security Agency. We did top secret things in secret locations with terribly proprietary electronics decoding signals that you're not supposed to be able to decode. I served 4 years in Berlin, Germany. And during that time, you were either into drugs, into photography, or into audio. My friends and I were into audio, and so we invested all of our spare change in audio components, and we would do the audio for parties, whether it was for the military guys or for the local Germans.
That work history that he had while in the military, then led to his fascination with power supplies. And obviously the natural extension of power supplies is what they're connected to.
I wasn't in audio, I wasn't part of the industry, I was just an audiophile, and I worked in the networking industry, making network devices and components. So the first product I created was for myself, which was a power distributor, because there was this huge weakness in commercially available products. You either had to use a power strip or you had to use a very expensive, quote, audiophile power conditioner, and all of these devices either had massive transformers and massive coils, and they were all trying to achieve the same thing. They were all trying to reject or eliminate noise coming from the outside. And in the research I had done, I had found that those approaches were limiting the ability of the components to draw current, number one, and number two, they were actually reflecting the noise generated by those components back into those components.
He knew intuitively that what connected power supplies to the electrical mains had the capability of improving the performance of electronics in a dramatic fashion through that work in the military.
My dealer at the time said, well, there's some power cords on the market and they seem to make a difference. So why don't you look into that and see if you can apply the principles that you applied to your prototype power conditioner and see if you can make a power cable. And I thought about it for a moment and I told him, I don't think I can really do that, but I'll look at it. So I worked for months and months with different designs, with different types of materials and foils and different dielectrics. And eventually I did come up with a product that was better than the ones that existed in the marketplace at the time. So that then became the first product that I made. And then this dealer liked it so much that he said, hey, can you make 10 of these? Because I'd like to sell them to some of my very important customers. I said, okay, if I got some spare time, I'll put some together. And it evolved from there, where so many people started coming and so many people started asking, can you make products for us, that I had to get rid of my full-time job, and then my hobby became my full-time job.
It was me, him, and his mother, actually. We started out in a 3-car garage, and we were building cables out of his garage, and we weren't building nowhere near the volume that we are now, but, we'd build, 10 cables a day and it'd be a good day's work. So we made it work like that, and over the years we've gotten bigger and we've had to get more employees, we've had to get bigger facilities, and
we were just lending products to people that wanted to use them for trade shows, for CES. And through that exposure, people began talking about us.
The product itself, it is its best salesman. The intent being that if we provide a really great product at a fair price, that one person would tell another person who would tell another person, and therefore we would be successful based on that.
Shinyata Research is a specialized company building products that are specific to signal and power transfer and making those products at reference caliber levels, meaning that there's no compromise to parts, no compromise to materials, and no compromise to the goal, which is to provide the absolute best performance possible from whatever system happens to be in front of the end user.
Every tech builds a power cable from start to finish. He's responsible for every aspect of that cable. And it helps them, knowing their signatures on the backside of that cable. It helps them take pride in the overall performance and the cosmetic quality of that cable.
Now, I do think it's important that things are well built with craftsmanship, and they're built to last, and that's what we do with our products.
Kalen's philosophy is that, in addition to creating products that are at the very pinnacle of performance, but also making sure that those products are accessible to people that don't have thousands upon thousands of dollars to spend on what they may perceive as the best cable product.
I don't create a product specifically designed for a marketplace or a price. I designed them to solve a problem. What really bothered me in existing systems was this overriding noise that would ride the music signal. It wasn't like it was background noise or hum or hiss. It's this grainy, gritty sound that was superimposed onto the music that always reminded you that this wasn't real, that it was coming through an electronic component. Shunyata is a Sanskrit word, and it means the stillness or the emptiness from which all creation emanates. So that word in itself describes at once my perspective and the products that we create. We're in a constant state of R&D. I'm always researching new materials, new techniques. There are many things that we do. Some of them we patent, some of them we publish and tell people, some of them we keep secret. Cryogenics, in the early days of cryogenics, it was one of the performance advantages that we kept secret. But as more and more companies discovered the benefits of cryogenics, it was no longer important or even necessary to keep that secret, so we just chose to reveal this is what we do. You take risks. I've created whole spools of wire, and when you create an experimental type of wire, you don't get to make 5 feet. You get to make 10,000, 100,000 feet at a time, so it's expensive to create a different design when you're talking about wire. But I would say that I've had many more failures than I've had successes. So the successes come hard.
What Kalen's doing that's very different is he's actually building real scientific advances into the designs of the products, and that's evidenced by the number of patents he holds.
I made a breakthrough in the fundamental way in which you transmit a signal across a conductor.
The Zytron signal cables in particular has made the biggest difference of any product or any series of products in our company's history. There's been this progression in his design capability over the years that I think right now, more than at any other time, and the products that he's developed now more than any other products in our history, represent a pinnacle of performance and price that we've never enjoyed before.
Hello, I'm Calen Gabriel with Shinyata Research, and this is the Hydra Typhon. Today what we're going to demonstrate is the electrical characteristics of the Typhon. Well, specifically the lack of reactance of a Typhon. Conventional power conditioners use filters that are composed of capacitors, inductors, transformers, and these all have characteristics, impedance curves, and they can be reactive with different types of components, especially amplifiers. So what we're going to demonstrate here today is the lack of capacitance and the lack of inductive reactance of a Typhon. I have a Hioki impedance analyzer here, and this will allow us to look at the resistance, the capacitance, and the inductance of the Typhon. I'm going to turn the Typhon around so we can access the port on the back. And let's just move the impedance analyzer, put it right up on top of the Typhon so that you guys can see it easily. So let's zoom in a little bit here, and you'll see on this menu, right now it's set for, okay, hold it still there, Mino. There we go. Right now it's set for total impedance, and we're going to set it for capacitance. And now we're going to take the probes and we're going to connect them to the neutral and the hot of the Typhon so that we can get a reading. Now if you look at the display, you can see that the analyzer's searching. It's trying to find a capacitance reading, and it's having trouble doing that. So right now it's looking down in the picofarad range, which is very low. And as you can see, it keeps searching, gets confused, and starts all over. This indicates that it can't find any capacitive reactance of the unit. Now what we're going to do is we're going to disconnect it, and I'm going to change to inductance reading. So now we'll connect it back up again and see if we can get a reading on the inductance of the unit. And you'll see that the unit is starting its search. It's trying to auto range. It's searching all the different ranges. It's searching high, it's searching low, trying to find a reading. And as you can see, it's unsuccessful. In other words, it can't get an inductance reading. And lastly, we're going to disconnect it and change to resistance and see if we can get any type of static resistance reading off the Typhon. We'll connect it back up again. And you'll see it's auto-ranging, searching, and it can't get a reading. So essentially, according to our impedance analyzer, you can see that we can't measure capacitance, we can't measure inductance, and we can't measure a resistance. So effectively, the Typhon doesn't have any reactance, and yet it can dramatically reduce the perceived noise in an audio system. Thank you.